this is linear algebra, and this is part 1, this is chapter 1, which is introduction to system of linear equations. So linear algebra is a course that is it's been used in computer programs. It's been used in the concept has been used in face recognition and cryptography, machine learning. It has also been used in Python, in AI technology. So it's very important course that we can use it in our fingertips if you are studying software engineering or doing CS. So I'm doing, by the way, software engineering. That's why I want to share my knowledge with all of you who want to do some coding. So linear algebra is having, information in science, business, and mathematics is often organized into rows and columns to form a rectangular arrays. Array is the concept of programming. It is called matrices. Matrices often appear as table of numerical data that arise from physical observation. Obviously, we can make a matrix of any kind of numerical data that arise from physical observation. Important in developing computer programs or solving system of equation, because computers are well studied for manipulating arrays of numerical information. It is known as mathematical object. It has so many types of application like cryptography, machine learning, creating ranking algorithms in search engines such as in Google. There are types of linear equation. It could be a line having two unknown variables. It could be a plane having three unknown variables. It could have so many number of variables, unknown variables. Okay, and it will still represent a linear equation if it has a power of 1 each variable. These are non-linear equations. This one having a power of 2, this one is having a trigonometry, this one is the variables are being multiplied to one another, different variables, and it has under root. Homogeneous are those which have 0 on the right side, the constant variable, the constant variable. These are constant variables, only values. So if it is 0, then it is known as homogeneous, because it is homogeneous means it is passing on the origin, and if it is not 0, then it is known as non-homogeneous. Linear system, there are so many, we can have so many number of equations, and then we can just manipulate those equations. We just convert them into matrices, and then we try to find out whether it has a unique solution, infinite means solution, and or if it has contradiction. Okay, m means having a number of equations, having number of equation, n means having a number of unknowns variables. Okay, if we okay, so we have three types of solution. One solution is when we have two equation and they are intersecting to one another, and after their intersection we have only one intersection, we have only one point. This is known as unique solution, having the values. Okay, another example is when we have two parallel lines but they are not intersecting. We can call it inconsistent solution or system. The system has inconsistent solution. We can call it contradiction, no intersection, no solution. Or we could have two lines intersecting one another infinitely many times. So we call it infinite solutions. Okay. So if we have a unique solution and we want to write down the solution, how do we write down? We write down in this way. Having two values, having two unknown variables, x1, x2, then 3, 1 ordered pair. Having three unknown variables, then 3, 1, 7. Having n number of variables, then n number of times we try to write down in this way. Okay, whenever we get the unique solution. If we have infinite many solution, okay, then how do we try to represent the answer? For example, let's suppose that we have this equation. I'm just going to convert this in a matrix form. 16 minus 8 and 4 in a matrix form, and I just do Gauss elimination. We will understand what is Gauss elimination. For now, let us see. So I got these 0, and if we get these 0, then we can say that yes, this system has infinitely many solution. And now I want to show the answer. So I have this equation. These are two unknowns. One is dependent on another. Okay, so these two variables are dependent on one another. So we convert y is equals to s. We call the we have assigned a different variable which is s. We call it a parameter, and then we make x a subject, and then y is equals to s. So x is equal to 1 plus 2s upon 4. This allows us to express the solution by the pair of equation called parametric equation. We only do this when we have infinitely many solution. Okay. and then we try to represent the answer in this way: x is equal to 1 plus 2s upon 4 and y is equal to s. So this is for infinitely many solution. Infinitely many solution. So there are two types: solution inconsistent and consistent. Inconsistent is when we have contradiction. Contradiction, no solution, no zero solution. Consistent means we have two types: either one solution, unique solution, or infinitely many solution. Okay, one solution is the independent solution and dependent solution. Use primary equation to describe the solution set of the linear equations. Okay, so we have this equation, and it's saying that it has a infinite many solution. Use parametric equation to describe the solution set of the linear equation. Okay, so we will try to make x the subject, and then we assign different variables to these. Let's suppose x2 is equals to s, x3 is equal to t, or x4 is equals to w, assigned randomly, and then we make x a subject, and yeah, we have made x a subject. We have given different variables to each one as s, r, t, and after doing that we have show in this way. We can actually write down in this way, like this. So this whole thing is x1. Okay, so this is 1 upon 8 plus s upon 4. Okay, okay, s plus s upon 4 minus 5 upon 8 r and plus 3 upon 4 40. Then we can write s r t. This is how you try to write down in form of in answer, in the form of answer. So this x1, this x2, this x3, this x4, and this is the answer. Okay, so this is how we try to write down. We write down parametric equation whenever we have infinitely many solutions. Okay, write a system of equation with a solution. Okay, so it got the solution, it got a unique solution. So, and we have this we have to make two equation where we could have this solution. So it's easy. um, so this is x and y. Yeah, we can put here -3, and we can assign any kind of gradient, let's say 2, and we got 4 and plus c. Then we got the values of c, which is 4 to the 8. 8 will go there, so it will be -9, -10, -11. So it's going to be -11. So it becomes a different equation, like I've done here. I have put 1, I have given 1, I have given 2, I have put these coordinates, and here, in here I have got the value of c, and then I got two different equations which are intersecting on this point. So I have done this task, right? A system of equations. Okay, now we have understood about that there are three types of solutions: unique solution, infinitely many solution, contradiction. We understood about that which are linear equation and which are not, and we understood about that that we should be that this how we try to write down the answer. Now let's suppose we have these equations. So how do we try to convert this in a form of matrices? We convert them in this way, and we all know that these are constants. These are constant numbers. These are constants. Okay, these are variables, and this portion is known as augmented matrix. Okay, so there are other matrices as well. This is known as column matrix. This is a square matrix. This is a null matrix, row matrix, diagonal matrix, since it's in a diagonal form, like this. We have identity matrix, and we have scalar matrix. Okay, supposing that we have this equation and we need to convert this in a form of matrix. So first of all, we always try to write down in this form: A is augmented matrix, is x are the unknown variables, and B is a column of constant. A is a coefficient matrix, x is a matrix of unknown, and you can see here that these are, they are multiplied, right? So if you try to multiply, then x y z z z. So this is a standard way of writing down, and this is the augmented matrix. Next, we need to understand about algebraic operation and elementary row operations. Okay, we try after converting this in a form of matrices. Now we need to find the solution. What is the solution of this? How am I going to find it out? In order to find out the solution of any matrix, we try to do elementary row operations. So what are the elementary row operations? These are the basic method for solving a linear system. Perform algebraic operation on the system that do not, I repeat, I do not alter the solution set. It does not alter it. We do it in this way that we try to solve the linear system in such a manner that it does not alter the solution set, and so that we could find out what is the solution of that particular matrix, and that produces a succession of increasing simpler system. It makes it more simple until a point is reached when it can be ascertained whether the system is consistent, and if so, what its solutions are. There are three operations. Number one is adding a constant times one equation to another. Like you have the matrix, and you just, what you have done, like for example, this equation 1, this equation 2, this is equation 3, equation 1, equation 2, equation 3. So I have taken this equation and I have multiplied by -2, and then I have added to this equation, so it becomes like, so only this changed, right? Since I have only tried to change this, so I have multiplied by -2 and I have added here. Okay, yes. So this is one, this add a constant times on one, add a constant time one equation to another. Second is multiply an equation through by a zero constant, either through a row or by column. Okay, these elementary operations, they can be performed in row and in column as well. Supposing that I have taken in column, then I want to add a constant times one equation to, I mean one column to another column. I can do that. I can do it in a form of rows, I can do it in a form of column. It's your choice, but most of the time we try to do in row form, since we are dealing with equations, but it doesn't matter. Okay, second is multiply an equation through by a non-zero constant, which means multiply a whole row by a certain constant, non-zero constant. Like for example, I have multiplied the whole equation by 1 upon 2, and I got the answer. So doing this operation will not change the solution of the matrix. It won't alter it. The third thing is interchange two equations. Like row 1 come into the place of row 2, row 2 come into the place of row 1. Like I've done. Okay, I have done not. I have not done. But like for example, I have these equations, right? I can just, if I want to interchange, right, I could interchange to here and put this to here, and it will be different. For example, this would be 3x 6y minus 5z is equals to 0, and this would be 2x 4y minus 3z is equal to 1. So I have interchanged these two. Okay, so I can do that. Then what we have here is, so yeah, this is it. Right now I'm going to do the questions. Now question 1, write down a general linear system of two equations and two unknowns. So we have two equations, so, and we have two unknowns like x and y, so it could be write down like in this way: a1, a2, 1 and 2, and this is we have two equations, right? Each equation has 1 has each equation has two unknown variables. So it says two equations, so we made two equations and then we have two unknowns. These are two unknowns, so this is how we write down 1 1 1 2 2 1 2 2 x1 x2 x1 x2. Then second we have three equations and three unknowns. We got three equations and three unknowns. So okay, this is the equation of a line. This is the equation of a plane. We got three equations and we got three unknowns. Then the last one is two equations and four unknowns. So two equations but having four unknown variables. So we write down in this way: 1 2 3 4 4 unknowns, 1 2 3 4 4 unknowns, and two equations. We have a second equation. Second question: under what condition on A and B will the linear system have no solution, one solution, finite many solution? We have this. So we have been given this, okay, and I could just convert this in a form of a matrix. Okay, so let me convert this in a form matrix. So supposing I have this equation, so I'm going to convert it in a form augmented matrices matrix. So it's going to be like 2 4 minus 3 minus 6. This is the augmented matrix. This is the unknown matrix, and I got the constant, which is A and B. I'm going to play with this one. I'm going to put the operations like I have put. I'm going to use the first operation, which is add the constant time equation to another equation, right? So I'm going to do that. I'm going to write down like this. This symbol says that it has already the operation has already been taking place. This equation is R1, this equation is R2. So R2 plus R1 multiply by 2 minus 2. Okay. Okay, so whenever we try to write down the operations, we try to read from we start to read from here, that this is R1, it's been multiplied by minus 2, and it has been added to R2. Okay, so this is how we try to read it right here. This is how we write down the operation, that what it is going on. Okay, so according to this, I have multiplied this equation by minus 2 and I have added to R2, so it's going to be 0. Yeah, it's going to be 0. Since now it is 0, like I have in this form 2 minus 3 0 0, and this is A and B. Okay, okay. So actually, not only these, or not only the augmented method, but also the constant will also be used. So it's like this. A and B will also come. So A multiply by minus 2 and add to B, so B minus 2A. Okay, so we got A minus B minus 2A. Now supposing if I want to have a unique solution, but we cannot have a unique solution because there is no one. I mean, these are 0. There is infinite many solution because there are three solutions. One is that we have a unique solution, we have the values. The second is when we have 0 equals 0, and we have these kind of, on the left side it's all 0 and on the right side it's also 0, then it is infinitely many solution. Another form is when we have 0 equal to 1. If for example we have all 0 and we have 1 in here, then it is contradiction. But if we have 1 equal 0, or we have 1 equal 1, then we have a unique solution. That we have only any one in here, and 0 it is 1, doesn't matter, then we have a unique solution. But if it is equal on 0 on both sides, like 0 and 0 infinite, then it is infinite many solution. If it is 0 and this is 1, it is contradiction. But if any one of these is 1 and the other is 0 or 1, then it is a unique solution. Okay, same thing here. So right now, if this whole thing is 0, then it is infinitely many solution. How to make it 0? So it could be possible if only if I make this equal to 0, if I make this equal to 0, it's equals to b minus 2a. 2a is equals to b, and a upon b upon 2. So if it is if I put 2 in here, okay, so if I get b, if I have b is equals to 1, oh sorry, b is equals to 2 and a is equals to 1, then we can have infinitely many solution, because it would make it 0. The whole row is 0, then it is infinitely many solution. Okay, but if we make it um, if we have 3 and 1 or 4 or 1 or anything like that, which would make it non-zero, then it would be contradiction. Okay, so what I've done here is I've tried to simplify it, and so having these value, it would be infinitely many solution. Having 1 1 or 4 1 or 3 1, anything like that, and then it would be no solution, it would be a contradiction. Okay, it cannot have a unique solution. It is not possible, since these are these are 0. There is not a single one in here. Okay, we have another question. Each linear system has infinitely many solutions. Use parametric equation to describe its solution set. For example, we have this. Let me convert this in a form of matrices. So it's going to be 2 minus 3, and we have 1. Then we have 6 minus 9 and 3. Put this in a form matrix. You can see here that this multiply the whole row by 3 and add it to here. It would all this will be 0. So it's infinite many solution, and we can write down the parametric equation by, okay, let me just first of all write it down. This would be 0, because I have put made the operation like r1 plus r2 multiplied by minus 3. So okay, so actually this is r2 plus r1 multiplied by minus 3. So r1 is multiplied by minus 3 and added to r2. This would make it 0, and so this is infinite solution. And then we make x the subject, like this is 2x minus 3 equal to 1, right? So x is equal to 1 plus 3y upon 2. This is x. And as for y is dependent on x. So y, we put any kind of parametric variable like s. So this would become s. X is become like I've done here. I've made x the subject. I've taken the parametric variable t, and this become t. And then if I want to write down the answer, then it would be in this form, like x and y is equal to 1 plus 3 t upon 2, and then we have t. This is the answer. Same thing I have done in here as well. I have converted this. I will convert it in a form of matrices, or if I don't do that, well, yeah. So converting this in a form of matrices, and then I try to do the operations which make it 0, and also make this one as 0 as well. So having two 0 rows tells us that this is infinitely many solution. Okay, even if we have one 0 rows, it would still be infinitely many solution. And so we will make x a subject, and we assign parametric variables to x2 and x3. So x1 is make x1 subject, x2 is r, x3 is s. We put these, and we got the answer. Okay, Then we have the last question: find all values of k for which the given augmented matrix correspond to a consistent linear system. So we have this. Okay. So I have done the operations. I have multiplied this minus by minus 4 and I have make all of this 0, or maybe not. Multiply this by minus 1, this would be 0 only. K minus 4, so 8. Okay, 8. Okay, so this is 8, and okay, so this is not k minus 4 actually, it's been multiplied by 4, so it's more like 8 minus k4 since it's been multiplied by 4. Then we have this, 4 4 16, 2 plus 16, which is 18. So we got this. Okay, so now we have in this form 1 plus k is equal to minus 4, and then we got 0 plus 8 minus 4k is equal to 18. Okay, so now to okay, so it says consistent linear system, which means it is either infinitely many solution or unique solution. It is either infinitely many solution or it is unique solution. Okay. Okay, so right here, if I put 2 here, then it would be 0, and if all of these are 0 and this is 18, then it will make a contradiction. So any value of k except 2 would make a consistent solution, either it is infinite or unique solution. So any value of k except 2 would make a would make a consistent solution, like I've just done here. If I put 2 here, then it would make then it would make contradiction or make inconsistent solution. Consequently, for all values of k not equal to the given augmented matrix correspond to a consistent linear system. Okay, so this is this was chapter 1. You can say this was 1.1. This was chapter 1.1, and we will discuss 1.2 in the next video.